Ever get that feeling like you're staring at something super intricate, like one of those old school clock mechanisms,
Oh, yeah.
like all those gears and springs and stuff? It's like right there in front of you, but actually understanding how it all works together, how each piece contributes, I don't know, it can be kind of a head scratcher.
Definitely.
Well, that's kind of how I feel sometimes when we get deep into blockchain transactions,
Uh-huh.
especially with all these newer concepts popping up, like account abstraction.
A lot to unpack.
It is. It is. And that's actually exactly what we're going to do today.
Okay.
We're going to take apart those Ethereum transactions piece by piece. We're really going to focus on the life cycle of a transaction, from the moment you hit send all the way to it being permanently etched on the blockchain.
So we're not just looking at the parts list, but the assembly instructions as well. I like it.
Exactly, exactly. And we're going to look at it from two different angles.
Okay.
First, we're going to rewind a bit and look at the traditional way things have been done with what are called externally owned accounts, or EOAs.
Right.
Then we'll shift gears and dive into the world of account abstraction. We'll see how that shakes things up, what new pieces come into play and how the whole system operates differently.
Sounds like a plan.
So to make sure we're not just making things up as we go along, we've been digging into some really insightful stuff, like talks from Yoav Weiss. He's been a key figure in developing that ERC-4337 standard for account abstraction.
Oh, yeah. He's got some great insights.
He does, he does. And we've also been looking at presentations from the Ethereum Foundation and, of course, the actual ERC-4337 proposal itself.
Got to go straight to the source. Right?
Always, always. So our mission today is to really break down that transaction lifecycle.
Okay.
In both those worlds, EOA and account abstraction. Hopefully we'll have some of those aha moments along the way.
Those are the best.
They are. But, without drowning everyone in a sea of technical jargon.
Bringing that balance is key.
Absolutely. So let's kick things off with what we know best, right? Let's start with EOAs.
Right.
How does a transaction actually work in that world? What are the essential parts and how do they all come together?
Well, at its core, an EOA transaction starts with you, the user.
Right.
You decide to do something on the blockchain, like send some Ether or interact with a day app.
A decentralized application.
Exactly. And to authorize this action, you use your private key.
Like your digital signature, right?
Yeah, think of it like your unique stamp of approval.
Yeah.
Your wallet software then takes all this information and creates a transaction.
So it's not just a simple send this to that kind of thing. It's more structured, right?
Yeah. It's a package deal. It includes the recipient's address, any data you're sending along, maybe instructions for a smart contract, the amount of Ether you want to send, and a really important part called the gas limit.
Gas limit, right. So that's kind of like setting a budget for how much computational work you're willing to pay for.
Exactly. It also includes something called a nonce. It's essentially a counter for your transactions.
A counter.
Yeah, it prevents someone from taking your transaction and replaying it multiple times without your permission.
Oh, like a security measure.
Exactly.
Yeah.
And last but not least, the transaction includes your signature.
Generated using that private key we talked about.
Yep, that's how you prove it's really you initiating the transaction.
Gotcha. So we have our transaction all packaged up and ready to go. What happens next? How does it actually get onto the blockchain and become, official?
Once it's signed and sealed, your transaction gets broadcast to the entire Ethereum network.
So it goes out to all those computers, those nodes that are constantly working to keep the blockchain running, right?
Exactly. They receive your transaction, and then the scrutiny begins.
Scrutiny.
Yeah, they have to make sure everything is legit. They check if your signature is valid, if the nonce has been used before, if you have enough Ether in your account to cover both the transfer and the gas fees.
Like a whole bunch of checks and balances.
Yeah, to maintain the integrity of the entire system.
So it's like the network is saying, all right, prove to me you're allowed to do this and that you've got the funds to back it up.
Exactly. If your transaction passes all those tests, then it's eligible to be included in a new block on the blockchain.
And those blocks are proposed and added by, what are they called? The block proposers?
Right, yeah. Formerly known as miners.
Right, right. So once your transaction is nestled in a block and that block gets confirmed by the network, then it's official, it's executed, and it can't be changed.
That's right. It's immutable.
Now, with EOAs, that private key is really the heart of the whole thing.
It's the key to the kingdom, literally.
It is. It
Yeah.
is. But that also has some indications, right, when we think about security and user-friendliness.
Oh, for sure. This one key rules all approach, it's simple, but it's got its downsides.
Like what?
Well, managing that private key is a high-wire act. You have to keep it super secret so no one else can access your funds.
Right.
But at the same time, you absolutely cannot lose it.
Because there's no forgot password option.
Yep. And if you want to change your key for security reasons, it's not a simple update.
Ooh.
You essentially have to create a whole new EOA and transfer everything over.
That sounds like a hassle.
It can be. And then there's the fact that you need Ether to pay for gas for every single action you take.
Which can be a barrier for new users, right?
Absolutely. You need to have the network's native currency just to use it.
It's a bit of a chicken and egg problem.
Kind of.
So that's the EOA world in a nutshell. Now, let's shift our focus to account abstraction.
All right, time for something new.
We've touched on this a bit, but how would you explain the main idea behind account abstraction? And how does it try to address some of these limitations we just talked about with EOAs?
The big goal with account abstraction is to really bring smart contract wallets to the forefront.
To make them as powerful and easy to use as EOAs.
Exactly. Make them first-class citizens on Ethereum. The idea is to abstract away those traditional mechanisms that the protocol handles directly for EOAs.
You mean like the private key signing, the replay protection, and the gas payment stuff?
Exactly. Instead of the protocol handling all that, a smart contract, your wallet contract, takes on those responsibilities.
So instead of my private key being the single point of control, the logic for authorizing transactions is built into the code of a smart contract.
That's it. And that smart contract can have its own rules about who can authorize transactions and under what conditions.
Which opens up a whole bunch of possibilities beyond just using a single private key.
A whole universe of possibilities.
Could I, eventually get to a point where I'm interacting with the blockchain entirely through my smart contract wallet? No more needing an EOA to initiate things?
That's the long-term vision, yeah.
Yeah.
Right now, you might still need an EOA to initially set up your contract wallet, but the ultimate goal is to have your contract wallet be your primary interface.
So EOAs might eventually fade into the background as contract wallets become more popular.
It's definitely a possibility.
Now, account abstraction isn't a brand new idea, right? But this ERC-4337 seems to be making some serious waves, especially because it doesn't require changing the core Ethereum protocol.
You're right. It's been around for a while. But a lot of the earlier approaches needed complex changes to the core protocol.
Which is not an easy thing to do, right?
Not at all. It can be very disruptive. But ERC-4337 is different. It's designed to work within the existing framework of Ethereum. It introduces a new kind of object similar to a transaction and a separate pathway for processing them.
All without messing with the fundamental consensus mechanisms of Ethereum.
Exactly. And it's already live on testnets and even on mainnet.
So it's not just theoretical, it's actually working.
It's happening.
Okay, so if we're not using traditional EOA transactions in this account abstraction world, what is the basic unit of interaction? What do we call it?
The new kid on the block is called a user operation.
User operation.
You can think of it as a pseudo-transaction object. It represents the user's intent to do something, but the way it's structured and handled by the network is different from a regular transaction.
So what kind of information does it contain? Are there similarities to what we saw in a regular EOA transaction?
Oh yeah, there are some parallels in terms of the action itself. A user operation includes fields like to, which specifies the recipient, called data, which contains instructions for a smart contract, and fields like max fee per gas and max priority fee per gas, which are related to how much you're willing to pay for gas.
Okay, so the core elements are still there.
Right. It also has a nonce field, but the way it's interpreted is more flexible. And there's a signature field, but as we mentioned, what it means and how it's validated is different.
Right, the smart contract wallet gets to define how that signature is created and checked. What other key pieces of information are packed into a user operation?
Well, there's the sender field, which tells you which smart contract account is initiating the operation.
Right.
And then there's init code. This is where things get really interesting.
Init code?
Yeah, it contains the code needed to create the smart contract account if it doesn't already exist.
Wait, so with account abstraction, a smart contract wallet can basically bootstrap itself into existence as part of its first action.
Exactly. It's like self-creation.
Yeah.
The init code allows the wallet to be deployed on demand. Typically, this code would interact with a factory contract.
Factory contract.
It's a special type of smart contract that's designed to deploy new instances of a particular wallet implementation.
I see.
And these factory contracts might have their own rules, like they might require a stake to prevent spam or malicious deployments that could clog up the network.
That makes sense to have some safeguards in place. So we have our user operation all filled out. What happens next? How does it go from an idea in my wallet to something that actually happens on the blockchain.
The journey of a user operation is different from a traditional EOA transaction. It all starts off-chain.
Okay.
You, the user, interact with a wallet application that supports ERC-4337.
Maybe an existing wallet that's been updated or a brand new one designed for this?
Exactly. And through this interface, you create a user operation that describes what you want to do.
All right, so I've crashed in my user operation. What happens next?
This user operation doesn't go to the regular Ethereum transaction mempool where EOA transactions hang out.
Oh.
Instead, it goes to a special mempool just for user operations.
So there are two waiting rooms now.
In a way, yes. And this is done through a new type of communication with Ethereum nodes using what's called an RPC call named eths on user operation.
Eths on user operation, okay.
This separation is really important for how account abstraction works without needing to change the core protocol's transaction handling.
So there's this new mempool for user operations. Who's keeping an eye on it? Who picks these up and moves things forward?
This is where we introduce a new set of characters. Bundlers.
Bundlers.
Yeah, they're basically network participants. They could be regular Ethereum nodes or special services running alongside nodes, and they're listening to this user operation mempool.
They're the ones gathering these user operations.
Right.
Okay, what do they do with them?
Before they send anything to the blockchain, bundlers do a kind of test run, an off-chain simulation. They basically make a call to a very important contract called the entry point.
Entry point, okay.
They call a function on the entry point called handle ops, and they give it the user operation they've collected.
Like a sneak peek.
Sort of. It lets them quickly check if the user operation is valid, like if the signature is in the right format, and if it looks like you can pay for the execution.
Oh.
If a user operation fails this initial check, the bundler might just toss it out.
So it's like a first line of defense to catch any obvious problems before things even reach the blockchain.
Precisely.
What happens if a user operation passes this simulation?
If it looks good, the bundler takes it to the next level, the on-chain phase.
Oh, okay.
They gather up a bunch of these seemingly valid user operations and bundle them into a single, regular Ethereum transaction.
So one regular transaction can contain multiple user operations.
Exactly. And this single transaction, made by the bundler, is designed to call that entry point contract we talked about.
The one they did the simulation with.
The very same. Specifically, it calls the handle ops function on the entry point, and it feeds it the whole bundle of user operations as data.
Okay, so this one transaction carrying a bunch of user operations gets submitted to the Ethereum network and eventually arrives at the entry point contract. What happens inside the entry point? How does it handle all these bundled requests?
This is where the magic of ERC-4337 really comes into play. The entry point processes each user operation in the bundle one by one, going through a series of checks. This is called the verification loop.
Verification loop, so it's a more thorough on-chain validation of each user operation.
Exactly. For each one, the entry point first checks if the sender, that smart contract account, already exists on the blockchain.
Okay.
If it doesn't, and the user operation includes that init code we discussed, the entry point will use that code to deploy the account using a factory contract.
So the account can be created on the fly as part of processing the user operation if it's the first time it's being used. That's pretty neat.
It is. It's very efficient.
What's next in this verification process?
The next crucial step is that the entry point actually makes a call to the sender smart contract account itself.
It calls the account.
Yeah, it calls a function on the account called validate user op. And this is where the unique logic of that particular account kicks in.
The code within the smart contract wallet gets to do its own checks.
Precisely. It can verify the signature using whatever method it wants. It can check the nonce according to its own rules. And it can make sure there are enough funds in the account's deposit held within the entry point to cover the gas costs for this operation. At this stage, the account also tells the entry point how much it needs to pay, the required payment.
So the smart contract wallet itself is saying, yep, this user operation looks good to me and I've got the money to pay for it.
Exactly. And there's more. If the user operation has something called a paymaster and data field, it means that a third party, a paymaster, might be sponsoring the gas costs.
Paymasters can pay for gas. That's huge for user experience, right? Especially for new users who might not have Ether yet.
It is. It's a game changer. It opens up possibilities for dApps to subsidize gas or let users pay with different tokens. So if there's a paymaster involved, the entry point checks if the paymaster has enough funds and calls a function on the paymaster contract called validate paymaster user op. It's basically asking the paymaster, Are you okay with covering this transaction?
So it's another layer of checks and balances.
Exactly. And finally, as part of the verification loop, the entry point makes sure that either the account itself or the designated paymaster has enough of a deposit within the entry point to cover the gas costs for the whole operation.
Okay, so after all these checks, if a user operation passes with flying colors, what happens next? How does the action actually take place?
If all the user operations in the bundle have gone through the verification loop and everything looks good, the entry point moves on to the execution loop.
Execution loop.
For each validated user operation, the entry point calls a function on the sender smart contract account, usually something like execute user op or exec from entry point. You might see different names depending on the implementation.
Okay.
And it gives this function the user operation data, which then triggers whatever action was intended, like transferring tokens or interacting with another contract.
So the action itself is defined in the user operation.
Yep, in the call data field. And importantly, during this execution, it looks like the smart contract account is the one doing the action.
So when my smart contract wallet interacts with another contract, it appears as though my wallet is directly making that call.
Exactly. Now, after the execution, if there was a paymaster involved, the entry point might call a post-op function on the paymaster contract. This lets the paymaster do some cleanup after the main action has happened, like maybe refunding any extra tokens that were pre-charged for gas. Finally, the gas used by the whole HandleOps transaction, including all of the verifications and executions, is paid by the bundler who submitted it. The entry point then takes the fees that were collected from the accounts or the paymasters and sends them to a beneficiary address specified by the bundler.
So the bundler gets rewarded for their work.
That's right. It's an incentive to keep bundling and submitting user operations.
It's a pretty intricate process, a lot more steps than a standard EOA transaction.
It is more complex, but this complexity is what unlocks the flexibility and those new user-centric features that account abstraction brings to the table.
Right, it's a trade-off.
And just to add, there's also the idea of more flexible nonce handling within the smart contract account itself.
So the account can have its own way of managing nonces.
Yeah, it doesn't have to stick to the simple sequential model used by EOAs.
Interesting. All right, we've now walked through the whole life cycle of both EOA transactions and these user operations. Let's zoom out a bit and highlight the key differences between these two approaches. How do the pieces fit together differently?
The differences are pretty significant, and they touch on several key stages.
Okay.
First, there's the initiation of a transaction. With an EOA, you directly sign a transaction using your private key.
Right.
But in account abstraction, you create and sign a user operation using the logic defined within your smart contract account, which could involve all sorts of different signing mechanisms.
So the way you authorize a transaction is fundamentally different.
Absolutely. Then there's the validation phase. For EOAs, the Ethereum protocol has built-in rules for checking signatures and nonces, and every full node on the network does these checks.
Right.
With account abstraction, those validation rules are actually defined and executed within the code of the smart contract account itself during that validate user op call we talked about. And it's all orchestrated by the entry point contract. Paymasters can also add their own layer of validation if they're sponsoring the transaction.
So it's like the rules for what constitutes a valid action are now programmable at the account level.
Exactly. Another big difference is in gas payment. With EOAs, it's simple. The sender has to have ETH.
Right. Account abstraction is much more flexible. Gas can be paid from the account's pre-deposited funds in the entry point, or it can be completely covered by a paymaster.
Which opens up a whole new world of possibilities.
It does. Users could potentially interact with dApps without ever needing to own ETH.
That's a big deal.
It is. We also talked about bundling.
Right, bundling those user operations.
EOA transactions are usually processed individually. But with account abstraction, bundlers play a crucial role in collecting multiple user operations and submitting them to the entry point as a single transaction.
Which can save on gas fees overall.
Exactly. Another key difference is in security. With an EOA, everything hinges on the secrecy of your private key. If it's compromised, your account is vulnerable.
Right, that single point of failure.
Account abstraction allows for much more sophisticated security mechanisms,
Yeah.
all defined by the smart contracts code. You could have things like multi-signature authorization, social recovery options, or different, potentially more secure signature schemes.
So the account itself can be more secure.
Exactly. And finally, there's the difference in nonce handling. EOAs use a simple sequential nonce managed by the Ethereum protocol. But with account abstraction, smart contract accounts can implement their own custom nonce logic.
which could be more flexible.
Exactly.
It's amazing to see how account abstraction really reimagines so many fundamental aspects of blockchain interaction. It feels like more than just an upgrade. It's a paradigm shift.
I agree. It's a whole new way of thinking about and using accounts on Ethereum.
So what are some of the biggest aha moments or those really intriguing possibilities that account abstraction opens up?
Well, the fact that a smart contract account can pay for its own creation using the init code, that's huge.
Right, it makes onboarding so much easier.
Exactly. And then there's the flexibility and authentication. We're not limited to a single private key anymore. You could have things like social recovery, where trusted friends can help you regain access if you lose your key,
Oh, that's a good one.
or multi-sig, where you need multiple approvals to authorize a transaction.
Like a safety net.
Exactly. Or per device keys, which can enhance security.
So you could have a different key for your phone and your computer.
Exactly. And then there are session keys, which are only valid for a specific app for a limited time.
That's interesting.
It's great for convenience and user experience. Like, imagine playing a blockchain game where you don't have to sign every single action.
Yeah, that would get old fast.
It would. And then there's the whole world of gas abstraction and sponsored transactions. dApps could subsidize gas for new users, or users could pay for transactions using different tokens.
So you wouldn't even need ETH to get started.
Exactly. And we could see things like upgradable wallets, although we have to be careful about the security implications there.
So wallets could get better over time.
Right. And some people are even talking about plug-in stores for smart contract wallets, where you could add all sorts of cool features.
Like app stores for wallets.
That's the idea. Ultimately, account abstraction is about putting smart contract wallets on an equal footing with EOAs, and maybe even making them the dominant form of account on Ethereum.
That's a pretty exciting vision. So as we wrap up our deep dive here, what's the most important thing we should take away about how account abstraction fits into the big picture of blockchain transactions?
The key takeaway is that user operations follow a different path than traditional EOA transactions. They start off-chain, hang out in a separate mempool, get bundled together by bundlers, and then land on the entry point contract, which handles the on-chain verification and execution.
And all this complexity is what enables those new features and possibilities.
Exactly. It's a significant evolution in how we can interact with dApps and manage our assets on Ethereum.
Absolutely. So as we finish up, what are some things our listeners might want to think about or explore further based on what we've talked about today?
I'd encourage you to think about how these changes might affect the future of dApps and the overall user experience. How might gas abstraction or more flexible security lead to new types of applications or wider adoption?
Good questions.
It's also worth checking out specific ERC-4337 compatible wallets like Argent and others that are coming out.
Right. See how this is actually being implemented.
Exactly. And it's worth digging into the security aspects of the entry point contract itself. That's a critical piece of the puzzle. And keep an eye on how paymaster services develop. They could revolutionize how we pay for transactions and onboard new users.
Some great areas to explore. It definitely feels like account abstraction is changing how we think about accounts on Ethereum, moving away from the old key pair model towards something more intelligent, more customizable, and more user-friendly.
Absolutely. It's an ongoing evolution that's changing the very definition of an account on Ethereum, and it's full of potential for innovation.
It is. It is. So to everyone listening, stay curious.
Stay curious.